Okay, so now we've got the expression for our Green's function. Our Green's function solves the differential equation in the green box. We now want to integrate over P naught using the residue theorem. Okay, so let's take a look. So first of all, let's draw in. So this is the complex P naught plane. There's the P naught plane. And let's put in our path of integration. So our path of integration, where do we integrate from? Well, from minus infinity to plus infinity. So that's where our path of integration will look like. Okay, so what's the first thing that we have to do? So the first thing that we need to do, we need to close our integration contour. You see, we can only apply the residue theorem with a closed contour. But now there are two possibilities that we need to consider. So let me just draw them both in. This is again a complex P naught plane. Now, and again, what's our integration path? Well, it's over there. That's how we're integrating. Now, what should we do? The one thing we could think of doing is closing the path in the upper plane, or we might decide to close the path in the lower plane. So let's call this option number 1, and let's call this option number 2. And the question that we have to answer now is, should we do 1 or 2? So 1 or 2. Okay, so let's first of all take a look at what is the difference between 1 and 2. Well, along this integration path, P naught will actually have a real part. Let's just call this PR, and it'll have an imaginary part. Let's call it IPI. And the difference between 1 and 2 is that on path 1, the imaginary part is greater than 0, whereas on 2, the imaginary part is less than 0. So the difference between paths 1 and 2 is in the sign of the imaginary parts. Okay. What decides whether we close as in 1 or as in 2? Well, we want to make sure that the contribution from the piece of the contour at infinity, we want that to be equal to 0, because then we can freely add it to our result. So if the contribution, the extra contribution shown in 1 will be closed in the upper half plane vanishes, then we should use 1. If it vanishes in the case 2, then we should use 2. Okay, so how do we tell whether it vanishes or not? Well, look at the integrand that we're integrating. There, we've got a product of two things. The first thing is I over P naught squared. So in fact, that's a power, and it's a power going to 0. So if we look at our integrand equals a power, and that's the 1 over P naught squared. But then what are we multiplying? We're multiplying by an exponential. And the exponential might be going to 0, or it might be going to infinity. Well, you know that an exponential always beats a power. So the power here is trying to go to 0 because it's an I over P naught squared. So it's going to 0 as 1 over infinity squared when P naught goes to infinity. But we need to look at what the exponential is doing, because if the exponential is blowing up, then that tiny suppression by the power just won't matter and the integrand will blow up. Whereas if the exponential is dying, then we know that the integrand vanishes extremely rapidly at infinity and we'll get no contribution to the integral. So let's take a look at the exponential. That's the thing that we have to study. What does the exponential look like? Well, we've got e to the I P naught tx minus ty minus I p dot x minus y. And let me plug in the complex P naught. So we'll have e to the I, we'll have the real part, PR, tx minus ty, and then we will have minus pi tx minus ty minus I p dot x minus y. What I've done is a trivial substitution. Okay, so I've just plugged in what P naught was, a very trivial thing. But what we can look at now, what is determining how the exponential behaves? Well, the only piece of this that is irrelevant is the e to the minus pi tx minus ty times by, and I'm just going to put dot, dot, dot. The only relevant stuff is what I've shown you there. So if we are looking at possibility 1, then we know that pi is greater than naught. And if tx minus ty is greater than naught, then the exponential goes to 0 exponentially fast, because we've got e to the minus pi, which is huge on this contour. We've gone off to infinity. And tx minus ty is positive, so e to the minus a very large positive number, that exponential is decaying. If we're also on path 1, so pi is greater than naught, and if tx minus ty is less than naught, then tx minus ty is negative, then that means that this exponential is e to a positive number. So in this case, then the exponential actually grows. It'll go to infinity as we take pi to infinity. So it does not go to 0. What about contour 2? For contour 2, we know that pi is less than naught. So in this case, if tx minus ty is greater than naught, then the exponential will blow up. Why? Tx minus ty is positive, pi is negative, so e to the minus pi tx minus ty is e to a positive number. Well, that exponential is going to blow up as we take pi to infinity. You see, if you're sitting here at infinity, then almost everywhere on this contour, pi is infinitely big, and either positive if you're on path 1 or negative if you're on path 2. But pi is massive, okay? And then finally, if we're on in situation 2, so that pi is less than 0, and if tx minus ty is less than naught, then pi is negative, tx minus ty is negative, and we've got e to the minus negative times negative. It means e to the minus something. So in this case, the exponential is going to 0. So what do we learn? Actually, if tx minus ty is positive, then we should close as in path 1. And if tx minus ty is negative, then we should close as in situation 2. So for path 1 over here, we can say exactly when we need to do this. So let's clean a little bit of space. We don't need this anymore. We finish this argument. So path 1, this one situation, we will do this when tx minus ty is greater than 0. And what about situation 2? Well, we'll close as in situation 2 when tx minus ty is less than 0. So actually, which contour we choose to close in depends on whether tx is bigger or ty is bigger. Okay, good. So we've now decided how to close our contour. And we know because the exponential is decaying and because we've got an I over p naught squared, that the integrand is going to 0. And that means that the contribution from infinity vanishes. So we know how to close the contour so that the contribution from infinity vanishes. So good. Now we've got our closed contours. What we now need to ask ourselves is, where are the singularities? Because we want to know what are the residues inside the contour. So where are the singularities? Where are the poles? Where are the singularities? And the singularities will be where that denominator vanishes. So it is where P naught squared minus P dot P minus M squared is equal to 0. And that means that P naught must be equal to plus or minus the square root of P dot P plus M squared. What is that? That is plus or minus omega P. Now, this, guys, is bad news. And it's bad news because our poles are sitting on the real axis. We hit our poles at a real value of P naught. So because the poles are sitting on the real axis, are they inside the contour or are they not inside the contour? You see, they're actually sitting on the contour. So do we include the contribution from these residues or not? This is the reason why I said that these singularities make the integral ambiguous, because you now have to decide, should you include the contribution of the pole or not? Which pole should you include? Which pole should you not include? Now, actually, Feynman has solved this problem, okay? So we are going to use Feynman's prescription. And what Feynman said is, Feynman said in this original expression over here, you should add plus I epsilon, and epsilon here is infinitesimal. So this is often called Feynman's I epsilon prescription. Okay, let me just write it here. It's often called Feynman's I epsilon prescription. What this I epsilon in the denominator does, it pushes the pole just slightly off the real axis, and it might push it up or it might push it down. But because it pushes it off the real axis, we no longer sit on the axis and the integral becomes well defined. Now, okay, so first of all, how would we even know if this is the right thing to do? Well, to know whether this is the right thing to do or not is, with this prescription, we are going to check that using Feynman's prescription, the time-ordered correlation function is actually equal to the Green's function. And we'll see that those two are equal. And because they are equal, that is the proof that Feynman's I epsilon prescription is the correct way to treat the poles. Good. So now let's see what Feynman's I epsilon prescription does. So if we now look for the poles, we should modify this. We should say plus I epsilon is equal to 0. So that's the first modification. What is the next modification? Well, it's here in the square root. We need minus I epsilon. And remember, epsilon is infinitesimal. So we can expand this to first order in epsilon and forget about all of the remaining terms. So let's do that, okay? So this will be equal to plus or minus the square root of P dot P plus M squared. And then we've got a square root of 1 minus I epsilon over P dot P plus M squared. So what is this equal to? Well, this is plus or minus. This is omega P. That's what P dot P plus M squared is. And then if you have got the square root of 1 minus X, and X is extremely small, this is 1 minus a half X, and then there's order X squared that you're dropping when you do this, okay? So that square root over there, we can write 1 minus I epsilon. This is 2 omega P squared, and plus order epsilon squared. But we said we don't even have to bother about the epsilon squared. That's absolutely negligible. So what do we get? We get plus or minus omega P. and then minus plus I epsilon over 2 omega p. The exact size of the imaginary piece simply doesn't matter. All it's telling us is where the poles get shifted to. So you can see that if the pole has a real part that's positive, then it has an imaginary part that's negative. So there would be a pole sitting over here at omega p, and because it gets a small negative component, it gets shifted down. There will be another pole sitting here at minus omega p, and because the real part is negative, it gets shifted slightly up. And here, exactly the same thing. The pole at the negative value will be shifted slightly up, and the pole at the positive value will be shifted slightly down. So when you close the contour in the upper half plane, you should pick up the residue from the pole at minus omega p. And when you close the contour in the lower half plane, you should pick up the residue of the pole at omega p. So the next thing that we're going to do is we're going to evaluate what these residues are. And then we'll be able to calculate the integral using the residue theorem.